Hello everyone, welcome to the new lecture, and in this lecture we are going to discuss classification methods in GIS and why basically classification, because sometimes you might be having continuous data and you want to discretize the data. That means you reduce number of classes. For example, you might be having a digital elevation model where digital elevation values might be varying between say 1000 meter to 5000 meter. Now you want to give certain categories, or you want to create a discrete classes for this map, say relief map kind of thing, then you go for discretization, that is classification. And there are several methods which are available. 6 methods so far have been implemented in standard GIS softwares. So, we will discuss all those 6 methods very quickly. And basically the purpose here is changing a continuous data into a discrete data. That does not mean that it can only go with the raster data. It can also go with the vector data, especially the polygon data, and examples we will see from both raster as well as polygon data. And now basically, as I have mentioned, that the purpose of classification in GIS is first is to make the continuous data into discrete data, so that it becomes easier for reading and understanding a map, and to show something about the area which is being studied that is not self-evident. Sometimes you would like to hide certain things and highlight certain things, and you want de-emphasize something, and for that purpose also the classification can be used. There are 6 classification methods, and one by one we will go. That equal interval, natural breaks, then a quantile, equal area, standard deviations, and more recently it has been added is geometrical interval, which is quite useful. So, let us have first equal interval. Example is shown here. There is a data which is in continuous fashion, a digital elevation example is here, and at equal interval it has been divided, and then it has got now the 3 say classes in this particular example, or rather 4 classes, and the appearance of the continuous data into 4 classes, when it is discretized, it changes completely, and therefore the interpretation has to be accordingly. So, that equal, as name implies, that equal interval, that means if you are having a loaf of a bread and you want to slice down that bread. So, general practice is each slice is having equal thickness. Similarly here, that each class is having equal range of your values. In this particular example, the cell values. So, the equal interval method divides the range of attribute values into equal size subranges. Then the features are classified based on those subranges, and this is how the equal area is. The next one is the natural breaks, or it is based on the Jenks formula or Jenks optimization technique, and this method identifies breakpoints, as name implies, natural breaks. It identifies natural breaks between the classes using a statistical formula which is based on Jenks optimization technique, and this method is not as simpler as a equal interval. This is little complex, but basically it uses this Jenks method of minimizing the sum of variance within each of the classes, and natural breaks finds groupings and pattern inherent to your data, and this natural breaks concept is not only in GIS but also exists in case of grading of marks of students. Exactly in the same way it is done, that natural groupings are found using the natural breaks, and then for different groups and different grades are assigned. The third one in this category of classification from continuous to discrete is the quantile method, as that method, each class contains the same number of features, basically say based on frequency. So the quantile classes are perhaps the easiest to understand, but they can be misleading. Example here is that the same input digital elevation model is here, and then few classes have been generated here. So now it may give a completely different appearance of a continuous data. So that is why it is mentioned that it may be misleading. Now in if we take in say for polygon example, the population counts as opposed to the density or percentage, for example, are usually not suitable for quantile classification because only a few places are highly populated, and one can overcome this distortion by increasing the number of classes. So if you increase the number of classes, probably you are going backward. So for all classification techniques are not suitable for all types of data. It depends on the data, and therefore appropriate classification technique has to be adopted. If it is a digital elevation model, then it depends on your requirement one and what kind of variations of elevation values exist within a file, within a DEM. Accordingly, you will choose the appropriate classification technique. Quantiles are also best suited for data that is linearly distributed, and generally may not be, the data may be linearly distributed, maybe in a Gaussian fashion or a normal distribution, then accordingly a different classification technique has to be adopted. Now the fourth one is the equal area, and this method classifies polygon features by finding breakpoints so that the total area of the polygon in each class is approximately the same. As name implies, equal area. So instead of having equal interval, now you are looking the equal area, and in polygon it is possible to achieve this thing. And these classes are determined with the equal area method, are typically very similar to quantile classes when sizes of all the features are roughly the same, and equal area will differ from quantile if the features are of vastly different areas. Now this fifth one is standard deviation. Standard deviation, in this method the mean value is found and then class breaks above and below the mean at the interval of either 1/4, half or 1 standard deviations are placed until all the data values are contained within the classes. And this is a very standard practice in case, or a standard understanding in case of standard deviation. So that is also employed, and further values are aggregated. Those are beyond 3 standard deviation from the mean into 2 classes, greater than 3 standard deviation above the mean, and less the 3 standard deviation below the mean. So likewise you get we will see the example almost all example together and see the differences, how they appear differently, the same input map, how they differ when used for while using different classification technique. Last one in this series of classification techniques, that is the sixth one, is the geometrical interval, which has been recently implemented in the GIS softwares, and this classification scheme where the class breaks are based on class intervals and that have a geometrical series. And the example is here, which again the same map is, when it is subjected to geometrical interval, may have a different appearance. Now here in this geometrical classification, the geometric coefficient is the classifier, can change once it is to its inverse to optimize the class range, and algorithm which creates these geometrical intervals by minimizing the square sum of elements per class. So that means the variation within classes should not be much. That is the main aim here, and this ensures that each class range has approximately the same number of values with each class, that has that the change between interval is fairly consistent. And this algorithm was specifically designed to accommodate continuous area, especially for continuous area this is very suitable. and it produces a result that is visually appealing and cartographically comprehensive. That means that not only the output maps through this analysis looks okay, but cartographically also they are fine. Now it minimizes variance within the class as already mentioned, and can even work reasonably well on the data that is not normally distributed. So when data is normally distributed, then again one should choose another type of classification technique, and this classification method is also called smart quantile. So it's a variant of basically quantile classification technique. Now the 5 examples are here together. One is equal interval, equal area is not here, equal interval, quantile, natural breaks which is based on Jenks optimization, geometrical and standard deviation. As you can see here that see this, when equal interval has been chosen, the number of classes in all 4 examples except in standard deviation, their number of classes are 7. Otherwise here all number of classes are 5. So if we compare these 4, equal interval, quantile, natural breaks and geometrical, see the appearance of the same polygon map is completely different, though number of classes are constant, they are 5 only. As you can see that in equal interval, that 3 to 5, 3 to 6 one class, 6 to 9 is another, 9 to 12 and so on and so forth. But here in quantile this is changing depending on the basically the frequency, and in natural breaks again groupings have been identified and accordingly the data has been these classes have been assigned. In geometrical interval, as discussed, the technique has been used, and standard deviation. So you are having a in middle you are having a standard deviation here which is all, and the center point is 0 and then minus plus values are here and different class. So say the input map is same, input polygon map is same, different techniques will produce different results though number of classes might be same. So this one has to remember. The original, one important thing here to mention is that original data will remain intact. This is only for your visuals. Original data will not change. Of course, once you are satisfied with a certain type of classification, you can create a separate data set, or you can save that particular classification technique associated with that data set. So whenever next time you want to use, you just open that small file which is having this classification information, rather than creating a new data set with new classification based on new classification. Apart from these 6 classification, manual classification can always be there. That instead of going for computer to decide the classes, you can also decide, and which also called manual or custom classification, that a manual classification is done to emphasize a particular range of values such as those above or below a threshold value. Like for example, in this input digital elevation model, a higher, very high elevation points were required to be highlighted and rest were not required at all. Maybe because of in flooding, if inundation occurs, we know that water can reach to up to certain level, and so what are the areas which would remain safe during that kind of flooding is reflected here, and rest of the area will get inundated. So that is why manual manual classification can also be employed to highlight specific areas, specific elevations range, and then de-emphasize the others which are not really useful in that sense. For example, here that one may want to emphasize areas below a certain elevation level that are susceptible to flooding. Now I will give you one example of classification techniques in the real example how it can be used, and this we have used some years back using a census data and that data and related with an earthquake event, and how we can look towards the future, how this data can be used, having a information about a earthquake, and how we can look towards the future. So this is how one can employ the classification techniques as well as data, and some futuristic scenarios can be presented. This example is based on an earthquake which occurred in Latur, and as you can see that these are the rural houses in percentage, and this is equal interval classification. What basically is rural houses means there are two types of houses when the census is done, and it is recorded whether it's a engineered house which is having say columns and beam and steel and other things, or made from mud or bricks or stones. So we put them as those houses as rural houses, and engineered houses are urban houses. And you see that in Latur, that category even in equal interval classification, it comes under this 70 to 80%. So say 75% of the houses in this district were rural houses, and large number of deaths have occurred during that Latur earthquake of 1993. Now later on what it was found that when this earthquake occurred, some seismologists predicted that there might, because this occurred along this Narmada Son lineament, so people predicted that there might be some propagation, and then earthquakes in some other districts may also occur. So that was the main discussion. Later on the same lineament, another earthquake occurred, which is in Jabalpur, and see the same way the data was analyzed. Here what you see that the percentage of rural houses is relatively much less. It is about 45%, and because of majority of houses were engineered houses, and therefore there were only few deaths. Relatively in case of Latur, the number of houses in rural category were of about 75%, and therefore large number of deaths. So using a simple data set, one can analyze that what has happened in case of Latur, and what would happen in case of some other district if at all earthquake occurs. So for example, that earthquake occurred in Jabalpur, if that would have occurred in other districts, neighboring districts, then again we might have reached to the same roughly 65 to 75%. And this is what the predicted, that this Narmada Son lineament is going, and this the earthquake might occur in these districts. If those would have occurred say in Khargone, then 70 to 80% of the houses were rural houses. Number of death would have been almost same as in case of Latur. Even if this Jabalpur earthquake, instead of occurring here along this Narmada Son lineament, if it would have occurred in Khargone district, then similar scenario like Latur would have happened. But luckily instead it occurred in Jabalpur, where number of rural houses are relatively less compared to engineering houses. So using a simple concept, you can think that this is what the predictions were there, that now the next earthquake after Jabalpur would occur in Khargone, and this Jabalpur earthquake occurred in 1997. So this is the scenario, that in rural population, urban population, rural houses and urban houses, and rural houses in Latur were about roughly of 80%, whereas in case of Jabalpur just 56%, and few deaths, thousands of deaths. If the similar magnitude earthquake instead of Jabalpur or instead of Latur would have occurred in Khargone, then 84% of houses were at that time were rural houses. So relatively, if assuming that same density of populations, same number of people exist in that area as in Latur, more number of deaths would have occurred. Now using a simple analysis in GIS and the data which is almost available freely through the census department, such scenarios can be presented to decision makers. Why? Because this is what the future has to be looked, because now we know that all this Jabalpur, Khargone, all these districts are falling all along the Narmada Son lineament. An recent earthquake in 97 Jabalpur has occurred. In future there might be some earthquakes may occur in any of these districts. If at all it occurs, then some measures, probably there is a time to take certain remedial measures, educate the people, and may go for retrofitting or other thing. So, starting from a simple classification technique, even an equal interval can be employed to look these scenarios, which can give us some insight of what is going to happen in future. And that brings the end of this particular presentation on the classification techniques in GIS for continuous data to convert them to discrete data. Thank you very much.